Hello everyone, it's really honored to be here, and I'm very happy to see a lot of people around here. Introduce some of the latest advances. Of course, it's not all of them, but it's related with a current trend in atomic force microscopy manufacturing. So I will give you some of the little bit of introduction. But I'm not going to include any real basics of AFM. So if you have some doubt or have any questions on AFM technology, so we are around, our staff and myself, so you can come to me at the coffee breaks, and then we will answer to you all the questions. So actually, many people, you all probably all know that one of the first the scanning probe microscopy, scanning tunneling microscopy, was awarded the Nobel Prize in 1986. But not many people know that actually the atomic force microscopy, atomic force microscope was invented in Stanford University, and then in Professor Carcage's group. And then sadly, Professor Carcage passed away this year, July 6th. And then many scientists kind of gave the memorandums in the lot of papers, also including the science. So they give out beautiful stories. And so because of his contribution, so there's many applications and the areas are using AFM actively, like material science, polymer science, and graphene, solid-state physics, nanomanipulation and manufacturing, nanolithography, nano-optical science, and energy solar cell research, electrochemistry, also cancer stem cell research, and nanomedicine. So these topics actually presented 2 weeks ago in European NanoScientific Europe symposium. So it's covering a lot of territory right now. And I also found one of the kind of a strange application of AFM. So AFM is also come as a drama item or movie items like this. It was presented in CSI, it's a famous drama, scientific drama. But of course, the AFM is not able to make pictures when you put papers into the machine. But anyway, it comes out as like this. And but the AFM has many good things, but there's also many kind of still, because it's a young science and the young technology, it's still growing. It's a little bit about 50 years younger than scanning electron microscopy. So it has really the kind of a good high resolution, but accuracy-wise and repeatability-wise, it's kind of low reliabilities. So when we see this kind of AFM pictures, we can see the nanometer details of the structures. But we are wondering, because there are so many artifacts can be included, like a noise and drift and scanner artifact and so forth. So when we see this circle, is this the real shape of the structure we are seeing? So we become wondering. So when we go to the this kind of thing, so this is really excellent tool in relative dimensions, but it's not the conventional AFM was a kind of a weak one for the absolute dimensions. When we see these structures, it's a very nice AFM picture. So when we see these A and B, so it looks like A is taller than B, but if people ask that A is taller than B in the one picture, then we can answer those questions. But if this height of A is a certain micrometer or nanometer, then it's difficult to answer because of the low reliability. And if we measure these structures separately, and then it becomes harder. So is A really taller than B, and then it's really hard to answer. That's the big kind of how can I say hurdle for us to go to the it's good for the academic research, but it's really hard to go into the industrial applications. So there's many directions in SPM development. Like especially in university, they are kind of developing a lot of things. So using AFM or SPM technology to kind of measure different kind of properties and things. And us also kind of doing this kind of researches. And then this afternoon, Dr. Jay Kim will present about the scanning electrochemical microscopy or SECCM and different application too. But as a company, there's another direction. So we, as a company, we are researching in how to kind of improve the fundamental system integrations, like system stability, accuracy, speed, ease of use, and these kind of things we are focusing on. So as a POC systems, our definition of ideal AFM is AFM without scanner artifact and tip wearing, and the AFM that can measure absolute dimensions with a high repeatability. So people can use this instrument to control the processing or manufacturing and so forth. So in result, we kind of developed this kind of automated machine. It's a cost about $2 million, $0.2 million. Okay? And then, so it was listed as the 20 most promising semiconductor technology solution provider. So together with Terry Tenko. And also 1 month ago, we received the Prime Minister Award. It's the highest award for making instrumentation too. So now we go into what's the background to go into this area. This one is the AFM scanner. So we kind of conventionally people use the tube scanner. It's XYG together, but we separate this scanner X, Y, and G. And in here, instead of using just the piezo materials, we are using flexure hinges, and then those flexure hinges are pushed by this stack piezo. And then this one is pushing those flexure hinges to give out the scanner movement, and those movements are detected by the position detector. And then in result, we were able to minimize the out-of-plane motion, and also it give out great orthogonality on the images. And then in addition, after we separating the G scanner, also G scanner were able to react faster, and then it enables non-contact mode too. And in addition, there is another benefit. It's kind of one of the things that always vision comes together with the AFM, because AFM is great to see the very small thing, but it's hard to find the location to the thing that we want to image it. So vision system is always followed, but in vision systems, there's this kind of artifact, like bigoting. This is the non-uniformity of the illumination, and also there's a temporal white noise, and also there's a pattern noise in vision systems. So it kind of diminishes the ability of our vision system. So it's hard to find the place of what we are looking for. So this is original vision, and then so we developed kind of a vision enhancement system to find out the locations we want to see. So how we do that? So because since we separated the XY scanner, so this is first images, and then we move about 1 micrometer. So it depends on the structure we want to see. So we can change this movement scale, and we subtract this one subject second image from the first one, then we got this frame 1. And then we average this one to frame 1, 2, 32, and 512. Then we can see this kind of a structure. So this one is obtained by the 20x objectives. And then we still get down to 100 nanometer natural scan. So it's easy for us to find a place to look at. So we using this kind of the ability to enhance vision to utilize in optical defect inspection in LED wafers. So using this enhanced vision, and then we zoom in these places, you can see with the visions you can see this defect, and we can image this defect with AFM to analyze what kind of defect there is. So this is another benefit of separating the XY scanner to the G scanner too. So we utilize that, and then also those things kind of in wafer level, we can see we can detect the high defectivity and low defectivity. Those kind of valuable information to the manufacturers. Now so non-contact mode. So we are always pitching out the non-contact mode because it's not just one of the modes. Because of this non-contact mode, actually make possible for us to go into develop the industrial application like a semiconductor and so on. I'm not going details in how we do it to do the non-contact mode. But if you want to know how we kind of make a non-contact mode, you're welcome to approach me, and then I will explain those principles. But I just emphasize that in order to able to do this non-contact mode, this G scanner has to be controlled in amplitude-wise, like a plus minus 1 nanometer, and distance-wise has to be controlled within plus minus 2 nanometer, with about 5 nanometer sharpness with cantilever. So in order to achieve those things, like a low noise and fast G-solver system is essential. That's why it's realizing non-contact mode is so difficult. So about 10 years ago, when I go to the conference and then explain people about the non-contact mode, actually on the floor, the people, the professors and the high-ranking professors, they kind of raise a hand and then tell me they used AFM technology for more than 10 years, and then they tried non-contact, but it was impossible. So they are saying that you are making up. But now it has been proved and proved again. And so this way we prove it with the data, like with the non-contact mode with the 100 scan, and then we stay with the roughness measurement is stay same, and then we found out there is any tip damages actually, and then this is actually the test that industry do. So what this data is came from IMAP. What they do is they load the wafer, and then they align the wafer, and then go to the measurement site, and they do the survey scan, and then they approach again to the images, and then they take out the wafer. This is one time, and they do it 1,000 times to test it. So if the tip or measurement is reliable, so you can see this is an angstrom level here. So and this year, early this year, we also did this kind of a test. This is not 1,500, because this is 15,000 repeat measurement. The polished silicon wafer with a 10 Hz scan for 3 days. And then when you see this roughness measurement for 3 days, we can see getting the reliable data. So it proves that the non-contact really works. And then one of the other benefits with the non-contact mode, tip become more sensitive than normal mode. So it's not sensing the end of the tip, but it also sensing the side of the tip to climb up these steep walls. Because when we go into the like a semiconductor application, there are many the structures that like a sharp and sharp edges, and in conventional AFM, those structures easily break the tips. So you climb up easily, and then you see this kind of a high aspect ratio materials, and also tip also safe. So in our R&D, what we are doing is we are testing this every day, like with repeatability, and then we define the target, and this target was accomplished 3 years ago. So now we are taking the more the aggressive target. So this is angle repeatability, and those kind of testing we are every day in our R&D. So this is high repeatability too. And we are also we cannot do all this research ourselves. We are actively collaborating with our partners. This is one of the case. So Alex Weber from Lawrence Berkeley National Laboratory, they have all kinds of AFM. They trying to measure this solar cell materials. It's the hybrid halide perovskite solar cell. They want to measure short circuit current and open circuit voltage to calculate the efficiency of these solar cell materials, but they couldn't do it with the conventional AFM. And then, so they asked us to develop the technology so they can measure those things. So when they try to measure it, this sample is brittle, so they breaks or tip or breaks. So the data keep changing. So in here, so like a force distance curve, but the difference is it's real time and also high speed force distance curve. And then what is the important thing is we can control all the contact force, dwell time, and approach retract speed and retract distance, everything. We control everything to get optimize all the conditions. Why this is important, I will tell you soon. So using this the pinpoint mode, we were successful. We get beautiful images as well as adhesions and modulus and stiffness values quantitatively. And not just doing this mechanical property measurement, we are also doing this electrical property measurement. So when we go in, when we try to measure the conductive or current in the samples, in order to measure current, tip has to be touch the samples. So normal contact mode, they can measure this current on the samples, but there's always it's easy to include a topographical artifact. Or if we are doing just AC mode, like a tapping mode, then we cannot control the dwell time or contact time here, that current signal become really weaker. So, but with the pinpoint mode, we can control all the dwelling times, so we can optimize this signal to noise ratio. That way, we can optimize the images as well as we can optimize the data, current signals. So now we offer this technology to the Lawrence Berkeley lab, and then they will successfully measure those the perovskite cells, and then they published in Nature Energy, and they comment, very good comment on our technology too. Now we using broadening this application of a pinpoint, and this pinpoint we also include this pinpoint in our vacuum system, NX Hybrid, and then this can be used in a lithium-ion battery electrode to see the conductance and resistance, as well as stiffness and adhesions. And also, actually this year, I found out real increase the a measurement request on the piezo respond piezo force microscopy. So they are all include a new device or new memory device, and then they require those kind of a measurement. We found out this pinpoint mode really help on getting the really good data on piezo force microscopy. We also, there's two things we have to do, get the reliable data to get those kind of narrow trenches. One is to get the right cantilevers. So we are kind of also we are collaborating with the cantilever manufacturer to optimize the cantilevers. And then we are using this pinpoint mode. And then we found out that while they are doing pinpointing, we can also kind of detect this lateral force, how they interact with this cantilever and then sidewalls. That way, we can find out when it really approaches the bottom. And then also with the pinpoint, we found out we can minimize the interactions between sidewall and cantilevers too. So that way, we kind of achieve the successful imaging of the trench. And now we go into the I will give you some of our R&D activity in developing industrial application. One of the things is also the developing automations. So in this automatic machine, we are doing everything, like a measurement control, the focusing system, wafer handling, tip exchange, and everything we are kind of making automized in the system. Also, we develop this process comparability, like the cleanliness and also wafer size, and those or the in normal semiconductor laboratory institutions, they have a SECSTEM, those kind of protocols. We have to make our software to adapt to those protocols. It's kind of really the challenges. And also people are asking us to develop a different kind of instrument stages. And this is the machine for pattern sapphire substrate measurement machine. It has been delivered. So it has included 2 AFM, and inside it can host 6 cassettes of wafers. And with our softwares, so we can automatically deliver these wafers to both AFM simultaneously to improve the throughput of the measurement. So using this system, we are measuring this kind of structures and then giving out all the structural data to LED industry customers. And also display the area, display like a big panel. The manufacturers, they are using, this is about the big size of the quarter of this room, the big size, almost a room size machine. And inside, so we are adopting like a tip scanning head. So in head, it includes X, Y, also G together. So we can measure the big panels, because the big panels we can do the sample scan. And in every year, we are making about 4 to 6 special sample chucks for our customers, because this is the one of the challenges we took this year. This anti-warp sample chuck, because after all the patternings, when the device make this wafer starting as a flat one, but after making all this, after kind of going through all these complex processes, this wafer become like a somehow making like a warps piece, and then those warped wafer doesn't stay still on the stages. So that's why we are kind of making those special sample chuck for those the specialized wafers. Also, people are we are kind of attacking these problems. There's the particle problems in research. Academic research, it doesn't care too much about the particle problems, but when we go to the semiconductor industry, particles become really the big problems. We have to control those particles, and then not just in few years ago, we just take care of the front side, but now we are stacking these wafers. We also take care of the backside particle as well. So in order to control those things, we are kind of simulating all the airflow inside the system to see and then see this how these airflows go through and where the particle is generated. And then we optimize our system structure to help those airflow. And like this, so before this kind of irregularity of the airflow, so it produced all the those particles, but after the airflow is kind of well assembled, and then all the particle is not going onto the samples as well. So this kind of research we are doing it, and also with the throughput is important. So in every step we are calculating, optimizing, like sample loading. We count like 0.0 seconds to control calculate those times, durations, sample alignment, keep positioning, sample positioning, keep engaging to optimize all these processes to increase the throughput. Now also, not just doing those kind of things, we are also doing a lot of hybrid metrology, and many of them are kind of still confidential, but this is almost a kind of completed project, so I'm including it. So this is an AFM together with it's a WLI, wide light interferometry. So in measuring with the WLI here, and then it moves to the AFM to get the data. So we are kind of researching to develop this kind of a mode. The reason is that with the hybrid system, so we can see the hotspot using WLI. Like this is normal samples, and this is target samples, and then we can easily, when we subtract these images, we can easily identify this hotspot, so the place we need to look at, and then those areas we go into the AFM to analyze in detail to see what happens on that structure. So this way we can improve the kind of speed of the imaging dramatically. So this is optical vision of the kind of PTL measure of the ported recession. This artist head. And this one is imaged by WLI. It's 800 micrometer by 1,250 micrometer size images. And we zoom in with the AFM, and then we zoom in again to see the 10 by 10 micrometer to see very small these ported recessions. So this way we can generate images. So in summary, like a new AFM was developed to improve the scan accuracy and repeatabilities. And then true non-contact is not just one of the modes, it's really the important thing. We could go into the industry applications. And then I just skipped those parts. And then pinpoint mode, it looks like a simple, but we can kind of still we are kind of like widely improving or adapting this mode to solve a lot of problems in a lot of applications. And then more AFM applications for Windows are currently developing. And AFM will continue to evolve into more precise and versatile and user-friendly instruments. And in order to do that, we need a lot of collaboration and communication. That's the reason we are doing this kind of symposium. Thank you very much. Yes.
Do you have any questions for Dr. Cho? Is there any question from the floor?
Technically, what is the difference between normal contact AFM mode and this pinpoint mode?
Oh, so in contact mode, So in order to scan, so just a scan, it just travels, and then they kind of respond. They detect this tip sample interaction with the control with the by the servo system to image it, but we cannot control the contact time and dwelling time, and then we can once you determine the set point, and then certain forces will apply to the sample constantly, but you are not changing it. But when we see the samples, many samples are complex structures, and they respond differently from the force. So we need to control the force each point, and then we can control the contact time. So it's a dwelling time. So
is it controlled by the software?
Yeah, it controlled by software, everything. So right now we want to detect the current on this spot, and in order to get it, so in normal scanning mode, we just pass by 0.1 seconds. But in order to get right amount of in order to optimize the signal to noise ratio, we need to stay there 0.5 seconds. Then we can control it that way. That way we can optimize the signal to noise ratio, and then we can get best result.
So it is time taking compared to normal contact mode.
Right. So, but if you see the demo, so it's not that slow. It's kind of almost like a slow scanning mode, but it minimized the scanning artifact as well as other things. Yeah. So you should try to see. Okay.
Can we use this non-contact microscopy for transparent materials? For example, if we are fabricating some structures with a laser, for example, the ripples or concentric rings, then we can characterize these structures with the help of this non-contact microscopy?
Yes, of course. So that's one of the benefits of atomic force microscopy. So because that's the reason we are going to the LED industry, they have a reflective, or sometimes they have a transparent materials. So normal vision systems, they make errors, but we are using probe technology. So we don't actually see the materials whether it is transparent or not. So we can it's same for us. So with the non-contact mode, so we can detect it. That's why we also right now negotiate. Right now we are collaborating with the A company or M company. They are developing these real lenses, and those lens materials they have become really tiny and nanostructure. So they are kind of came to us to measuring those structures. So yes, this AFM can be used, especially non-contact mode on those structures.
Thank you.
Yeah, you're welcome.